In Part 1, we introduced the three main types of galaxies: spirals, ellipticals, and irregulars. In Part 2 of our exploration of the realm of the nebulae, we are going to look at the collective properties of these galaxies. Big galaxies are likely to encounter other big galaxies a few times over the course of their histories. The reasons this will happen is because the galaxies are, on average, only separated by about 10 or 20 times their diameters, making close encounters very likely. If you're in a crowded room where people are separated by only a few times your size, if you're running around blindly, you're going to run into someone at some point. But galaxies aren't moving around blindly. They're moving around under the influence of gravity, and that's the important difference. Let's compare this, however, the galaxy-galaxy encounters, to the encounters between stars within a galaxy. On average, within a galaxy, most stars are separated by 10 to 100 million times their diameters, so encounters are going to be extremely rare. It's only in the centers of the very most dense clusters of stars, perhaps in the cores of the densest globular clusters, that star-star collisions are likely to occur. But out in the outskirts of a galaxy, where most of the stars are formed and found, the average distance between stars is enormous compared to their diameters. Think about the Sun. The Sun has a diameter of about 1.4 million kilometers, and yet the nearest by star, Alpha Centauri and Proxima Centauri, are nearly 4 light years away, many trillions of kilometers away. The chance that two stars like Alpha Centauri and the Sun will collide are practically zero. Even if I took two galaxies the size of the Milky Way and bashed them together head-on, even though those two galaxy systems will collide, the individual stars within them won't come anywhere near each other on average. So galaxies are very different in the way they interact with their fellow galaxies throughout the universe. Their separations are small compared to their diameters, and so these encounters can be expected to happen not just once, but many times throughout their history. Indeed, galaxies can interact and collide, and when they interact and collide, this will boost star formation because gas clouds will be bashed together. Some of that gas will be funneled down into the central regions where it will feed their central black holes, and overall, the general collision and combination of stars, gas, and dust and dark matter in these galaxies can lead, as we shall see, to transformative mergers of the galaxies. We can't watch this by looking at an individual pair of galaxies. We have to consider the collective properties of galaxies to piece together the story of galaxy interactions. Here's an example. Here are a pair of spiral galaxies. Each of these individually is around the size of the Milky Way and Andromeda. They're two relatively normal-looking spiral galaxies, in this case separated by about 5 or 6 times their diameter. Not much is going on here. If I came back next year, or in 100 years, or even in 1,000,000 years, I wouldn't see them move very much, because galaxies move relatively slowly compared to each other. As a consequence, while these galaxies may be separated by 5 or 6 times their diameter, it could take nearly 1 billion years for the two of them to cross that distance on the chance that they are on a head-on collision. But many of these encounters may be glancing encounters. So we can't tell anything about the encounters of galaxies by watching single galaxies in the sky, but we see millions of galaxies around us. So we can go out and look and try to find pairs of galaxies that are in different stages of approach, collision, and merger. Here's how it works. We'll start with a pair of relatively bright spiral galaxies, much closer to each other than the Milky Way and Andromeda are to each other today. I can find another pair where they're starting to come closer together. Now they're within about 2 times their diameters apart. They're beginning to feel their mutual gravity, and the tides from one are pulling on the other, and vice versa. As a consequence, these tides are drawing out and enhancing the spiral arms. Spiral density waves can be very strongly enhanced by the tidal effects of a nearby companion galaxy as they begin to come together. Spiral arms, as we saw in the previous lecture, are the sites of star formation, and so star formation becomes strongly enhanced in these two galaxies as more and more stars are formed in these bigger and more prominent spiral arms. If the galaxies were to collide and pass through each other, they might look like this pair of galaxies right here. Here's a pair of spiral galaxies of similar size to the ones we've been looking at, but now they've actually passed through each other. Remember what I said about the separations between stars being about 10 to the 8 times bigger than their diameters. Two galaxies will pass through each other, but they don't pass through each other untouched. The gas clouds collide, form together and pancake, and begin to form stars at the interface of their passage. Their gravity and their tides begin to shred and pull the galaxies apart. What used to be spiral arms confined to the disk are now pulled out into gigantic and tidal tails in which stars are streamed and cast away into intergalactic space. Most of the stars stay in their parent galaxies, but now the galaxies take on a much more chaotic appearance. We can still recognize the spiral shape, but things are getting very, very messed up. These two galaxies have passed through each other and are now going to come apart, but now they're bound to each other and are going to continue to pass around each other. It's not so much a passage in the night as the beginning of a dance, a kind of a balletic pas de deux as the two collide, come, and dance and slowly spiral together. Even when they spiral together, it can take a long time. Here's two spiral galaxies merging together, their disks lit up with hot blue stars as they begin to furiously turn their gas into stars, and yet we can still recognize the disk shapes and the spiral arms crossing through those disks. We can even see the distinctive bulges, but that's not going to last for long. When the collisions get further along, their bulges, their spiral arms, and their disks all will shred and form into this massive, chaotic train wreck. Well, okay, galaxy wreck. What we see here is a massive galaxy wreck. In this previous phase, there's lots and lots of hot blue stars, but hot blue stars only last as long as 10 million years or so. After 10 million years, those stars will have gone supernova, and they will give up their gas to the surrounding galaxy and become neutron stars or black holes. When we get to this phase, the gas is being just churned up, turned into stars, but a lot of those stars formed at earlier phases of the encounter are now these evolved redder stars. And they're on enormously chaotic orbits, some going this way, some going that way. We see a spray of star formation up here as gas has been formed into stars and compressed. Down in the middle, we can see the beginnings of a massive burst of star formation. The centers are these hot blue train wrecks of stars and gas and dust. And in the near final phases, the two bulges have finally merged together. Their two black holes are spinning together down in their centers, and it will eventually become one big black hole. What's left of their interstellar medium is compressed down into the central kiloparsec, furiously forming stars in what we call a starburst. This is an extremely luminous galaxy, forming stars at an absolutely furious rate, trying to turn all of its gas that's left over into stars. It's a mess. The stars' orbits are going every which way. What used to be two galaxies is now one big mess of a galaxy wreck. Stars are orbiting chaotically on long elliptical orbits pointing in every direction, and the gas content is slowly being torn up and consumed, and eventually it will run out when there's no more gas left to form stars. We've seen this picture before, haven't we? A galaxy that contains very little gas and dust. It contains lots of evolved reddish stars, all on long elliptical chaotic orbits pointing in every direction in the direction of a spheroidal shape. Give it time for all these dynamical wiggles and wobbles to collapse and coalesce and settle down, and when it finally relaxes, it's going to become a giant elliptical galaxy whose mass is only a little less than the mass of what was originally two fairly big gas-rich spiral galaxies. But now it will be gas poor. It can't form any more stars because it formed all of its stars during the merger encounter, and we're left with an older population of stars on long elliptical chaotic orbits, giving this assemblage of stars its characteristic spheroidal shape. When viewed from afar, it's a giant elliptical galaxy. This is what I mean by transformative mergers. All galaxies were probably assembled through some level of merger process or another. Elliptical galaxies appear to be the products of these violent, massive mergers between two spiral galaxies, or maybe a merger between 2 or 3 or 4 or 5 more galaxies, all over the course of the galaxy's history. Galaxies go around together in space, as we're going to see, and this gregariousness, this tendency for galaxies to flock together, is what makes these transformative mergers possible. All galaxies, if they aren't now, will eventually go through some kind of transformative merger in the course of its life. And by all galaxies, I really do mean all, even the Milky Way and Andromeda. The Andromeda and the Milky Way are moving towards each other. Our mutual speed is approximately 500 kilometers per second. That sounds like a lot, and it is. It's faster than the 200 kilometer per second typical orbital speed of stars within the Milky Way and Andromeda. But remember, the Milky Way and the Andromeda are separated by 700,000 kilometers, or 700,000 parsecs. Excuse me, misspoke there. The Milky Way and Andromeda are 700,000 parsecs across, moving towards each other at about 500 kilometers a second. While that seems like a fast speed, it will take nearly 2 billion years to cross that distance. And when they do, well, there's going to be some fireworks. Here's an artist's conception of what's going on. In a few billion years, the Milky Way and Andromeda are going to merge, and we're going to make an elliptical galaxy, just like the sequence I showed previously. Here's what the sky looks like today. We see the mountains of the Earth super silhouetted against the bright Milky Way. And this little tiny smudge here, which is just barely visible to the naked eye, is the Andromeda Galaxy. Andromeda is, in fact, the most distant thing you can see with the naked eye on any given dark night, if you know where to look. Wait about 1 billion years, and Andromeda is going to be much bigger in our sky. And then bigger still, 2 billion years from now, and then the two of us will pass through each other and merge and collide. All of the gas and dust combined in the Milky Way and Andromeda, 10% of our mass of each of us, is going to be smashed together and begin furiously forming stars. We're going to, for a very brief period of maybe 1 billion years or so, be an enormous starburst in which the gas and dust of both of our galaxies is going to be consumed, making massive stars. We'll make one last pass apart, and then the two pieces will fall together, and in the course of about 6 or 8 billion years, begin to relax down and become a giant elliptical galaxy, where once there were 2 bright spirals, the Milky Way and Andromeda, in the nighttime sky. Mergers, as we've begun to recognize, play a key role in the evolution, transformation, and assembly of galaxies over cosmic time. They're very important for making Milky Way and Andromeda what they are today, and will be very important for making what the Milky Way and Andromeda will become in the distant future. We can't see this play out even on human timescales. 8 billion years is approximately how long it will take before this giant elliptical forms. 8 billion years is more time than the Sun has left in its life before it becomes a white dwarf, some 6 billion years in the future. So how can we possibly see what these stages are going to be like? We can do it because we understand how gravity works, we understand how gas dynamics works, and we have a pretty good idea of how star formation works. We can put them all together in a supercomputer and use computer graphics to see what the next 8 billion years of galaxy evolution will look like. The time is being read out in the lower right-hand corner of this animation developed at the Hubble Space Telescope Science Institute using a supercomputer simulation of the Milky Way, Andromeda, and the Triangulum Galaxy, here shown as they will be about 2 billion years in the future. The Milky Way and Andromeda begin a slow approach to each other. It's not quite a head-on collision at first. As they get closer and closer, they will begin to feel the tides from each other, eventually raising a bar where none was before in Andromeda, and splash together. The star formation in these splashes gives the galaxies a bright blue appearance in their disk, but the star formation will be quickly cut off, and the stars will grow red as they begin to evolve. They'll splash together again 5 billion years, and then splash and merge. The 2 black holes at the center of the Milky Way and Andromeda will merge together. Most of the stars will fall back in and will be left with no more star formation because there's no more gas and dust. The last stars have formed, and we have only the evolving giant stars and horizontal branch stars, giving this merged object an elliptical reddish appearance. The stars are on chaotic orbits. The disks are gone, replaced by chaotic elliptical orbits in all directions. What was once two giant spiral galaxies is now a single elliptical galaxy orbited by the tiny triangulum spiral and the multiple dwarf galaxies of the local group and assembly of galaxies that we live in. What will happen to the Sun and its planets? Well, 8 billion years into the future, the Sun will be a white dwarf, but our planetary system, at least the Earth and the planets outward, will likely still be intact. Will the Sun and its planets be part of this new giant elliptical galaxy? Or will they be part of that fraction of stars that are flung out into the cold of intergalactic space? We don't know the answer, but we can probably guess the odds. It might be as much as 50-50 that we'll end up in intergalactic space as we will end up part of this elliptical galaxy. The sky of the distant future of the solar system will be very, very different when we find ourselves living in an elliptical instead of a spiral galaxy. That the Milky Way and Andromeda are likely to have a collision in the next few billion years and become an elliptical tells us an important fact about galaxies. Galaxies are gregarious. Most galaxies are formed in groups or clusters consisting of many galaxies. They're like birds. They're more likely to be found in flocks than solitary galaxies out in the depths of space. Indeed, solitary, so-called field galaxies are relatively rare. Most of the galaxies are found in relatively small groups, and a smaller number are found in much larger clusters. What's the difference between a cluster and a group? A group consists of anywhere from 3 to 30 bright galaxies and many tens of dwarf galaxies. We live in a local group consisting of about 50 galaxies, with 3 bright galaxies and some 50-odd smaller galaxies. Clusters are gravitationally bound assemblages of between 30 and 300 or more bright galaxies and many hundreds to thousands of dwarf galaxies. The very largest clusters can have membership of up to 1,000 or more bright galaxies. The distinction, the dividing line between groups and clusters, is somewhat arbitrarily drawn at 30 bright galaxies. Although while it sounds arbitrary, a close examination of the properties in groups and clusters do show some distinctive properties, especially when you start getting into the larger and much more massive clusters of galaxies. So we're going to leave this arbitrary dividing line of 30 bright galaxies. That's 30 bright galaxies, not total galaxies. Even our own local group, which is a small group of galaxies, could contain, when a full census is completed, many hundreds of galaxies, mostly dwarfs. The sizes of groups and clusters range between about 1 and 10 million parsecs across, and we've cataloged thousands of groups and clusters in searches of the deep night sky. More are being found every year, and we're using them as signposts to find the most distant groups of galaxies to try to use them as signposts for the study of the evolution of galaxies across the cosmos. The local group is our home. It is the group of galaxies in which the Milky Way, Andromeda, and a third bright spiral, the tiny triangulum spiral, call home. It can approximately a megaparsec across, consisting of 3 bright spiral galaxies, the Milky Way, Andromeda, known by its name M31, and the triangulum spiral galaxy, known as M33. In addition, there are 2 bright irregular galaxies, the Large and Small Magellanic Clouds, that are satellites of the Milky Way. These are the 5 brightest galaxies that make up the local group. There are approximately 50 dwarfs as of the latest census of the local group, which when we combine these 50 dwarfs, the 3 bright spirals, and the 2 bright irregulars, brings us an approximate total mass of about 5 trillion times the mass of the Sun. Most of the mass of the system is in a combination of the dwarfs and the spirals. We do not yet have a complete census of the local group. The suspicion is there may be as many as 100 or 200 tiny dwarf galaxies, but they're very, very faint, probably only consisting of a few thousand stars. The search is on, and every year we find more and more of these as our search techniques are refined. The Virgo cluster is the nearest by cluster to the local group, and in many ways the local group can be seen as a small group on the outskirts of the Virgo cluster. It may be getting ahead of our story a little bit, but the local group appears to be falling towards the Virgo cluster. However, it has a long, long ways to fall. The The Virgo cluster consists of two bright elliptical galaxies. Note that these are bright ellipticals rather than spirals. These are M84 and M87, shown over in the picture on the right from the Hubble Space Telescope key project on the Virgo cluster. The Virgo cluster center, which we reckon to be the center of the brightest of these, M87, is about 18 megaparsecs away. So while the Milky Way and Andromeda as part of the local group are slowly falling into the Virgo cluster, we're still on the outskirts and are not part of it yet. The Virgo cluster is fairly compact. Most of the mass is found within the center 2 megaparsecs across, but the Virgo cluster itself extends out further because it's made of a larger assembly made up of smaller groups of galaxies that are found in the outskirts and slowly falling in. Overall, the census of the Virgo cluster is about 2,500 galaxies, most of which are dwarf galaxies, and a total census of all the stars, gas, and dust, including hot X-ray gas, added together, and estimates of the amount of dark matter from the motions of galaxies within this cluster, give the Virgo cluster a combined mass of 10 to the 14 times the mass of the Sun. That's 100 trillion times the mass of the Sun. But Virgo, while as big a cluster as it may seem and impressively massive, it's not the biggest thing we see out in the universe. Although extremely rare, the very richest clusters can contain many thousands of bright galaxies, including rare giant ellipticals, the most massive single galaxies we know of in the universe. These rich clusters can extend for 5 to 10 megaparsecs across, with masses of up to 1,000 trillion times the mass of the Sun. If you want, they're a quadrillion times the mass of the Sun. Ellipticals are always found near the center and are old, dead, and red. They aren't forming stars anymore, but they're enormous. Many of these can have individual masses of many trillions of solar masses. They can individually have masses which approach the mass of the entire local group. Spiral galaxies are found at the outer regions. They're still forming stars. They're distinctive because of their spiral shape and their bright blue colors from their hot young O and B stars. They're still actively able to form stars in the present day. These are the largest gravitationally relaxed structures that we know of. And indeed, the very largest clusters are actually only on their way to being gravitationally relaxed. They haven't gotten into their final or near final dynamical forms. Groups and clusters are dynamically relaxed. The objects inside of them are on the orbits they have, and the orbits are governed by and large by the collective gravity of all of their members. We call such objects gravitationally relaxed. They're not continuing to grow or only growing slowly compared to the dynamical times associated with the orbits of the objects inside of them. As you get larger and larger, however, the universe is not old enough for structures that big to have become fully gravitationally collapsed. The search for the extremely rare, very large clusters are finding objects that are just in the process of finishing their formation and relaxation in the present day. The universe is not quite old enough for the very largest clusters to have relaxed. But this is an important distinction. These are the largest gravitationally relaxed structures that we know, but they're not the largest mass structures that we find. Every structure we find of larger and larger mass from here on out in the universe are not gravitationally relaxed. They're part of the dynamic process of the organization of matter inside the cosmos. What are these structures? These are the superclusters. Superclusters are clusters of clusters, broad filaments and walls surrounding voids that are the largest recognizable structures in the universe. These structures range in size between 50 and 100 million parsecs across, with masses exceeding 10 to the 15 to 10 to the 16 times the mass of the Sun. The most massive object we know of contains 10 quadrillion times the mass of the Sun. The superclusters are largely found along long, thin filaments that occupy about 10% of the volume of the universe. What about the other 90% of the universe? That universe is in immense voids that are outlined by filaments and walls described by clusters and superclusters. The distinction? None of these superclusters are gravitationally relaxed. They are still dynamic and they are still forming. What their future is is a subject of great research and debate as we look at how structure forms in our evolving and expanding universe. This is a picture of matter on large scales in our universe, and we see that unlike in a galaxy or a cluster of stars, there is a distinctive upper limit to the structures. The universe organization of matter appears to be foamy, voids, large empty regions nearly, but not quite, devoid of galaxies, surrounded by broad filaments and walls consisting of many superclusters of galaxies. The universe on its largest scales takes on a very foamy appearance. We call this large-scale structure. The existence of large-scale structure is telling us important information about how galaxies form. These are large structures that are sculpted by gravity, and they are concentrations of matter where galaxies are in the process or were in the process of being formed in the distant past. But as much as this gives us information about the ways in which galaxies form, it does so by raising a lot of open questions. Why is it that galaxies only form in particular places? Why are they forming along the filaments and walls? Why are the voids so empty of matter? How empty are these voids? People are now making a census of the voids and finding that they're not 100% empty. They're not perfect vacuums. There appear to be galaxies in there. As we find these galaxies, it becomes of interest to study these galaxies. Do the few galaxies we find in the void have properties different from galaxies found in groups and clusters and superclusters? We're only just beginning that study. The final question is, which formed first, the galaxies or the clusters? Or is it something more complex together? Lots of open questions are raised, but we can see that galaxies form at their base the fundamental unit of the organization of matter. Galaxies are gregarious. They form into groups and clusters, forming the largest gravitationally relaxed structures in the universe. And above that, there is a next hierarchy of scale of the superclusters, indicating that the scale of the structure in the cosmos is a hierarchical system forged and sculpted by gravity.